All right. So, hello, everyone. Uh, my name is Patrick Donovan, and I run business engineering in the portfolio services group at JPMorgan Asset Management. And today I'm going to talk a bit about how we use Apache Ignite for high performance exposure management. All right, so exposure management. So today's talk, what I'm going to do is I'm going to go over one of our core computations in exposure management. I'm going to quickly review some of the key domain entities involved. And really, it's going to be a story about how we went about data modeling within Ignite and the different capabilities we could use to query that data. And really, the focus of this talk is going to be on read performance and our path to optimizing it for our use case. Ultimately, what we were looking for was very fast response times for this particular computation. So let's get into it. Just a second. All right. So let's start with what it is we're actually computing. What we call an exposure tree. So an exposure tree is essentially just a complex version of a pivot table. So anyone who's used a brokerage service or who's worked in the asset management industry will likely be familiar with these types of breakdowns. And one thing I'll say is that it's definitely a bit more than a traditional pivot table. So something like an Excel pivot table or a Pandas data frame isn't quite enough to cover what it is we're looking to do with our computation. And I've got here a bit of a contrived example, but it kind of gives you an idea of what we're producing. So we're taking a flat data set and we're grouping it together by certain attributes. And then we're aggregating up values. So something like the market value of a set of assets. We're also doing things like computing weights for each of those groups. And then we use those weights to produce sort of weighted risk metrics and ways for our investors to get a view into certain risk and return characteristics of their portfolios and benchmarks. And so the starting point for this computation really is those portfolios and benchmarks. It's the assets that we own, and the benchmarks are broad universes of assets and different asset classes, whether they be a stock benchmark or a bond benchmark. And one of the key things here is that the number of positions in these flat data sets can potentially be tens of thousands. They can get quite large. So it's important to understand the key entities that underpin everything before we go into sort of how we went about modeling it all in Ignite. And the three key data sets that I'm going to talk about today are positions, instruments, and analytics. All right, so let's take them in turn. Positions. Positions are essentially what we own in a particular asset on a given day. So a portfolio or a benchmark is really made up of just a number of positions. In the case of a benchmark, we call them constituents. But a position will have its own ID, and it will also be associated with ID. And so there's a one-to-one relationship between positions and the instruments that the instrument that is effectively represented by that position. An instrument will also have things like an amount, a date, and there's probably another 50 or so fields that make up that entity in our space. The next one is instruments. So instruments are one of our more complicated domain entities. And in our model, they're really the superset of fields that represent all the different types of assets that can be bought in the markets. So an example of a particular instrument type could be a stock, which has a particular set of fields that are relevant to it, or a bond. And then there's all sorts of different derivatives as well. So all of these sort of fall under the umbrella of what an instrument is. One thing to note about our instrument domain entities is that because it's a superset representing sort of a heterogeneous variety of entities underneath it, not every field is going to be populated when we push this data into our caches. It's really a sparse data set. And another interesting thing about it is it's really not a flat data set either. It's not just sort of a 300 fields. It's relational in nature. So I've listed a few sub entities within the instrument domain model, and these are things like identifiers or credit ratings, and these data sets can actually be temporal in nature. So certain values can only be valid for a particular date, for instance. And as I said, our instrument data model contains upwards of 300 plus data points. The final domain model that I'm going to talk about is analytics, and this is just a term we use to capture the sort of numbers that go into the number crunching. So an analytic entity will have an instrument. So there's a one-to-one relationship between a set of analytics and a particular instrument on a given day. And the numbers that exist within this entity are things like prices, yield, and there's actually many more, hundreds more. And these three pieces are really what drive the sort of core, the core inputs to the computation. So let me move on. All right, so data modeling. So when we first started looking at Ignite, one of the things that we really liked about the product and what was important was the flexibility and the co-location of data and compute. And when we first started out, we took a look at Ignite's SQL capabilities. And we also took a look at the JCash API. So talk a little bit about both of those. So again, just to set the stage, the core selling point here for us, at least when we initially approached Ignite, was that co-location of data and compute really is the killer feature for our use case. And one thing I want to stipulate up front is that the way we structured our data, we can be certain that all the data needed for particular computation is going to be co-located on the node that computation happens on. So while there's all sorts of nuance around distributed computations and data sets, in our case, we've structured it in a way where it's going to be in memory on that node, and they'll be co-located together. And this is going to be true for each approach that we explore. So whether it be SQL, JCache, etc. So what do we like about SQL? Well, the first is it has full DML support. So things like select and where. And this for us was really very developer friendly. Most of our developers have, quite a bit of experience writing queries in SQL. And so the learning curve was pretty shallow, and we thought we could be productive pretty quickly with this approach. Another aspect that we liked about SQL was the support for joins and indexes. So because our data is relational in nature and it often has a temporal element, support for joins and being able to put indexes on the time fields within our temporal data sets was really attractive for us initially. But we did run into a couple issues with this approach, again, in our use case. And before I touch on those, I want to talk a little bit about Ignite's memory architecture. So by default, Ignite will store the data within its caches off heap from the JVM that the computation is going to take place in. And this is for pretty straightforward reasons. You can have very, very large data sets, and having a JVM heap the size needed to hold all that data can introduce some things that we don't want to do, and certainly the designers at Ignite realize that. And so what happens when we query data in all these approaches, what we're doing is we're querying data that is managed off heap, and we're bringing it on heap to be used in the computation in some way. What's also nice about this is that transactional updates to that data, they happen off heap, and the next request that comes in that reads that data set is going to see the latest version of the data. And so one element of this computation, and all our computations really, is that we wanted them to be stateless. We wanted to pick up updates instantly and really have the complexity of managing the consistency of that data offloaded to Ignite. All right, so getting back to some of the issues that we experienced with the SQL approach in Ignite. And the first one was performance. So Depending on our data set, some of our query times were quick. They could be around 20 milliseconds for a relatively small data set and a small overall cache size. But for some of our larger data sets that were doing a lot of joins, these response times grew to be, more than a second, sometimes 2 or 3 seconds. And this was particularly true under load. And again, this may not be indicative of everybody's experience, but in our model and in the way we implemented it, these were sort of the response times we were seeing, and they weren't quite what we were looking for in terms of performance. So another issue that we sort of ran into was garbage collection pressure. So this is true of basically all our approaches, and we'll talk a little bit about how we went about dealing with that. But we're allocating a lot of data every request on heap in order to produce this computation. And so it's something that we always had to be mindful of in each approach that we looked at. So the next approach that we looked at was the JCash API. And what we liked about this was that it was just dead simple, right? It's key value, and it had really fast lookup times. So very straightforward approach there. The issues, though, that we ran into with the JCash API and our implementation were primarily around deserialization costs. So, as I touched on earlier, we have very large domain entities. I have lots of fields, and so deserializing these whole entities to have a fully sort of realized POJO is relatively expensive for us. It certainly allocates a lot, and there's a lot of overhead to that deserialization itself. And another aspect of the computation that I'll touch on is that each computation doesn't touch every data point in every domain entity. So while it's highly variable what data points are touched, it might be some subset of the data. So for instance, with our instrument domain entity, we've got 300 plus fields that are potentially relevant to the computation. And, in a typical request, we might touch 45 of those fields. And so deserializing the entire entity when we only needed a subset of the data felt a bit suboptimal. With the JCash approach in our testing, we also, similar to SQL, ran into some GC pressure issues. And this, again, was really just a function of how much we were allocating on heap with each request. So some other things that kind of came up in this approach was typical challenges that anyone might face when modeling relational data in NoSQL. So, we were taking certain strategies like duplicating data in multiple entities. And this, the approach here was about trying to avoid having to look up many entities just to reach a particular data point. We also split entities. So with our very large entities, we tried to split them down and be a little bit more surgical about how we were accessing subcomponents of those entities. But what ended up happening was we ended up with a quite complex data access code. Figuring out what we needed, when and where got complicated really quickly. So while we did like the simplicity, the JCash approach had some drawbacks for us. But that brings us to the solution that we ultimately landed on, which is Ignite's binary object API. So we just found this to be very flexible and performant in a really compelling way. And I'm going to talk a little bit about sort of binary object and the way we leverage it. So what is binary object? Binary object is at a basic level just an abstraction over the serialized data that's produced by the binary marshaller, the default binary marshaller in Ignite. One of the nice things about it is that this serialization format is pretty compact, and especially for missing data. And this is going to become relevant in a little bit. But if you have sparse objects like we do, having a compact representation of missing data fields it has a lot of advantages. Another nice thing about the binary object API is that collections are serialized and deserialized automatically. So, with our domain entities in this approach, we would take, the cache value, and we could actually attach lists or maps as fields within each cache value. And when you actually go to access these collections, it's very straightforward. There's nothing complex about dealing with them. They simply deserialize to a list of binary object or a map of binary object to binary object. So the last bit is the binary object API, which is really dead simple. Anyone who's used Ignite is probably familiar with getting a hold of an Ignite instance and calling the cache method to get a hold of an Ignite cache over the key and the value object. With binary object, you simply chain a method called to with keep binary, and what you get back is an Ignite cache that is generic over a binary object key and a binary object value. And then once you actually query the cache and you get a hold of some binary objects, you can access just specific fields and deserialize just a subset of that object using a very simple API, basically calling a method field on that binary object with a string that matches the field name. And in this case, I've kind of come up with another contrived example. You just cast it to long, and you've got a hold of that data. So I think it actually really helps to unpack what's going on under the hood a bit. And this really is kind of what we did. We learned a bit more about the serialization format, and it really led us in the direction of our ultimate solution. So what's going on underneath the binary object? And really, there's just one key data structure that we care about, and it is a byte array, and it represents all the data. And this byte array has three portions to it. One is a header, and these headers are relatively large. I think some 32, 36 bytes. Don't quote me on that. But one thing I'll also note is that we found information about this on the Ignite Confluence page, where there's all sorts of details about some of the implementation aspects of various parts of the system. And so they've got a whole lot of detail about what exactly goes into that header. And then you've also got the portion of the byte array that represents the data, and then you've got a footer. So what exactly happens when you access a field and ask for it to be serialized? Well, the first thing to understand is that field offsets, which is to say the index in the array where that field's data is located, are stored in the footer. So what happens is the string that you pass in will get hashed, and a field ID will be computed. And the hash function is based off schema ID, which is part of the header. And so it is context dependent. But once you have the field ID and you have the offset, you can quickly locate that data in the array. I mean, again, you don't have to do anything. This is what Ignite is doing. It's quickly locating that data in the array. And that data is prefaced by a byte that represents its type ID. So is it a string? Is it an integer? And then, of course, the bytes that represent that data itself. The last bit is that null, so a missing field, is represented just by a single byte. And so for sparse objects, missing fields are not very costly when you're bringing that binary object on heap. And really, every time we're querying data, what's actually happening is that Ignite is looking up the raw underlying bytes, and it's allocating these byte arrays, underneath each binary object on heap. And it's much more compact than a fully realized POJO, at least in our case. And so this has a lot of advantages that we'll talk about. Right. So designing on top of binary object. So we took a pretty straightforward approach. We would simply query the data, get back some collection of binary objects, and then we would wrap those binary objects in a domain object. And what this domain object would do is it would expose a developer-friendly interface. So I've just got a couple examples here, but you can kind of get the idea. For instrument, if you wanted to get the name or the currency, you would just call the getter as if it were a POJO. And what would happen under the hood is we would then delegate that call to the field method of the binary object and ask for it to be deserialized. And we actually took to calling this just-in-time deserialization. And this approach is really nice in a lot of ways, because what ends up happening is, just by programming naturally on top of it, sort of the optimal amount of deserialization just falls out of the back of it. So, to give you an example, if you have a conditional where you've got, whatever, 10,000 binary objects, and that conditional is only true for, say, 10% of them, and then you move on to access some fields underneath it, you're only going to pay the deserialization cost for the fields that you actually call into underneath that conditional. So what we found was this was really performant, and it was a really, really friendly way for our developers to interact with the underlying data. So performance numbers. What did it look like for us? A few things to keep in mind. These numbers are based on our specific use case. They're based on our schemas and our object designs, our hardware. So I don't want to give the impression that this is somehow going to be indicative of, everybody else's use case. But the numbers here, what I think is important is really their relative numbers. So, we just found that oftentimes binary object was an order of magnitude or more faster for most cases. And this was particularly true under load. It performed very consistently under load. And ultimately, the response times were fast enough where we were able to structure our computation in a way that when it eventually made it back to the user interface, it really hit that sweet spot from a UX perspective. We were looking to keep things under half a second to make the app feel snappy, and binary object effectively allowed us to do that. So I'm just going to touch on, in the last few minutes, here's some other considerations. So really, there's a couple things. One is around garbage collection, the other is threading. So any approach that we explored here is going to end up allocating a lot of garbage. And in our use case, even with binary object, we were doing a lot of allocation on each request. And anybody who's worked with and tried to optimize for a JVM garbage collector, there's really two things that you got to keep in mind. One is when you're allocating large objects, and one is when you're allocating long-lived objects. And so our approach to sort of managing this, allocating all of these byte arrays over and over and over again, was to partition the key sets. So if we had 10,000 entities that we needed to look up, what we would do is we would simply chunk each key set into, say, 500 keys. We would look up those 500 objects, wrap them in their domain, and then do the work that we needed to do on top of it, and then allow them to go out of scope, and then move on to the next set of keys. And what this did was it allowed things to stay very short-lived, which was friendly to the GC, and ultimately, we were able to see GC pause times that we could live with, and this was a pretty good outcome for us. Another thing I'll mention is the unit of parallelism. So, you may be tempted to add parallelism through thread pools and things, and we actually looked at this a bit to try to speed things up. But in our testing, the best approach for our use cases was to keep the unit of parallelism at the ignite callable level. So everything that happens inside an ignite callable is single threaded, and this includes iterating through those key sets, those partitions of key sets, and serially looking up data. The performance was so good that we didn't really feel the need to try to parallelize it any further. And what we also noticed was that there's a lot going on. Ignite manages several thread pools itself, the details of which are in the documentation. But if you introduce additional threading, you run the risk of introducing quite a bit of contention. And so we found that it's really best to just do things single threaded inside of ignite callable. The last little bit I'll mention is how exactly did we deal with temporal data, time series data? So, moving away from SQL, where this was a very easy problem with indices and where clauses, we had to figure out a way for us to, efficiently look up data that was temporal in nature. And the approach that we took was to simply store it in a list on our cache entries in sorted order. And of course, we had to bound this. We didn't want these lists to get too large. But what we could do was deserialize the object, or rather bring the object on heap in binary object form, and then binary search the list of binary objects and only deserialize the time element in order to quickly locate the index that we were looking for that particular element. And then we would bring the rest of the data out of the list to be interacted with in a more, fully realized way. So that's a nice little technique as well, if that problem is something you have to deal with. Right. So I'll just mention a few things to wrap up. The additional resources, the Ignite docs are really great, and we found them extremely helpful in this journey for us. One thing I'll note is that they actually explicitly say in the Ignite docs that one of the key advantages to SQL is when you're querying over distributed data sets. And because our use case was co-located, we weren't able to really take advantage of some of the power there in a way that a different use case might be able to. But there's also the Ignite Confluence website, and there's all sorts of documents that go into the design and details of various aspects of the system, the memory architecture, and in our case, the binary object format. And we just found these really valuable. I mean, I will say that there may be changes to the implementation that I'm unaware of, but most of what we talked about today is based off those documents. And I would encourage everyone to have a look at them. They've got a lot of great detail, and they really kind of help lead us to where we ultimately ended up. And we're very happy with it. And I think that's all I got.